Welcome back to the wonderful world of astronomy. We're in chapter 20, Galaxies and the Foundation of Modern Cosmology. And this video is part 2, Measuring Distances. In the last video, I talked to you about cosmology, that it is the study of the large-scale structure of the universe, so the vastness of the universe, both in space and time. As we study cosmology, we think about how large the universe is and also how far back in time the universe goes. In this video, we'll look at how we measure distances in the universe, and our assessment of distances is related to how long the universe has been around. So our assessment of space is related to our assessment of time. And if you think about on a simpler scale, you think if somebody says that they were driving for a few miles, and you can think, okay, so this person has probably been driving for a few minutes, and that would be different based on what speed they were going, whether they were on the highway or just going around town. But if someone says they drove for a few miles, you assess it's been a few minutes that the drive was. But if somebody says that they were driving on the highway and drove for about 120 miles, then you can assess, okay, this person has been driving for quite a while. And if it's on the highway, 120 miles, probably about 120 minutes, this person has been driving for 2 hours. And if someone says he's been driving across the country from Virginia, then that distance, you have a sense this person's probably been driving for many days. And that's a simple analogy, but it relates to how we relate our concept of distances in the universe to our concept of how long the universe has been around in time. So let's get into it. How do we measure distances? Here is from the Hubble Deep Field, all these galaxies, and as we've seen in previous videos, you see a variety of shapes. We see a variety of colors in these galaxies. And as we explore these galaxies, we want to know how far away are they? So how do we measure the distances to galaxies? You can see on this chart, it's pretty much a sum up of all that we're going to talk about in this video, but it starts from planet Earth. We have some methods, and here it says radar to the left, and I'll get more into that. And then there's parallax. You learned about stellar parallax back in chapter 15. And then stellar parallax is only good to about 1,000 light years. So we have other methods. And here we have Cepheids and distance standards and Hubble's law out to the edges of the universe, or the observable universe. And so we'll talk about all these methods now. Brightness alone does not provide enough information to measure the distance to an object. So we see a galaxy that looks very bright, and that in itself doesn't tell us anything. If you look at this picture here, it says these street lamps can serve as standard candles because they all have the same luminosity. So let's look at these. The one on the left is bright. It's the brightest. And then there's the middle brightness, and then the dimmer one. Now, if these were stars in the sky, that would tell us nothing about their distances, because stars come in all different luminosities. However, in this picture right here, assume that we know that all of these street lamps have the same luminosity. They're all the same, let's say 1,000-watt light bulbs. So the one that looks brightest to us, we know is the nearest one. The one in the middle is twice as far away, so it appears 1/4 as bright because the brightness falls off mathematically with the distance squared. So twice as far away means it's 1/4 as bright. This one on the right is 3 times as far away. It appears only 1/9 as bright as the one on the left. So if we know that all of these lights are the same luminosity, we can assess these relative distances based on how bright they look. Let's talk about now the first way that we measure distances in the solar system. We determine the size of the solar system using LIDAR, which is light detection and ranging, and radar, which is radar detection and ranging. And this involves, in the case of, you see the moon right here, we bounce electromagnetic waves, we shoot them towards the moon, bounce off, we get the reflection, and we can time how long it takes for that reflection to get back, whether it's LIDAR or radar. And we get this to very good precision. We know the speed of light, and so we can calculate the distance. And we can do this to other planets as well. And by the way, long before we had LIDAR and radar technology, astronomers were able in the 17th century to pretty fairly well estimate the distance to the sun. I think it was in about 1675 that the distance to the sun was estimated to be pretty close, about 94 million miles. Now, there was some guesswork that was done, and the guesswork happened to be correct. But they had a good assessment of the distance to the sun, even back in the 17th century. Now we move out into the galaxy, the distances to nearby stars. In chapter 15, you learned about stellar parallax, how we use the Earth's position at one time of year, the Earth's position 6 months later, and we get these two different vantage points to look at a star, and we see the slight little shift in that star. So this is what's called stellar parallax. It's good out to several hundred light years, about as much as 1,000 light years. But remember that the galaxy has a diameter of 100,000 light years. So 1,000 light years doesn't really cover that much distance in the galaxy. However, what is important is within 1,000 light years of us, there are several tens of thousands, if not hundreds of thousands of stars by which we can use stellar parallax to accurately determine their distances. And even though in the realm of the entire universe, that's not that many stars, it is important that we can measure accurately the distances to those stars, and then we can use those distances to build other methods of determining distances of things farther away. Which brings us to the idea of a standard candle. This is a vocabulary word I'd like you to know for astronomy. A standard candle is any object whose luminosity we can determine without measuring its distances. So basically anything that we know what its luminosity is. For example, we know that any G2 main sequence star, a G2 5-star, has a luminosity of 1 solar luminosity. Remember that G2 5, that's what our sun is. And we know that anything of that spectral type is also the brightness of the sun. For another example, a K2 main sequence star is 0.37 solar luminosities. Any K2 star is 0.37 solar luminosities. Now, we know that because we have used stellar parallax to measure the distances to many G2 stars that are in our vicinity, and we can measure their luminosity. We can tell what their luminosity is. Let's go back, as I explain what I just said, to chapter 15. Remember that there's a relationship between the apparent brightness, the luminosity, and distance. And you saw this picture back in chapter 15, that we have a certain amount of light that gets put out by a star, and after 1 astronomical unit, a certain amount of light covers, let's say, a square meter. And after 2 astronomical units, that amount of light that passed through 1 square meter gets diluted. It's less brightness because it's spread out over 4 square meters. And if you go up to 3 astronomical units, it's spread out even more. So the star light that hits your eye, if you're out at 3 astronomical units, it's not going to be as bright because the light is spread out more. You saw this equation in chapter 15, and I told you you'll be seeing it quite a bit throughout the semester. Very important equation. That the apparent brightness, how bright it looks to the observer, is the luminosity, which is the amount of power put out, divided by 4 pi times the distance squared. The importance of this equation is that you've got 3 quantities here. And using algebra, if you can know 2 of the quantities, you can solve for the third one. Now, apparent brightness, with our technology, we can always measure that easily. That's using something called a photometer. It measures how bright the star looks. Now, if we know the luminosity, we can tell the distance. And that is based on this equation. A little bit of algebra brings us to the equation at the bottom of the screen. Distance equals luminosity over 4 pi times brightness square rooted. Or there's another version of this equation. If we know the distance and we know the brightness, we can solve for luminosity. So here's how it works. How do we know that all G2 stars are one solar luminosity? Well, because within about 1,000 light years, we have many, many G2 stars. And I'm just picking on G2 as an example because that's what the sun is. I could be saying any spectral type, M5, for example, but I'm picking on G2s for now. So we look at a bunch of G2 stars, and we know their distance by stellar parallax. We can measure their brightness, and then we can solve for their luminosity. And what we have discovered is that all G2 stars have the same luminosity. All M7 stars have the same luminosity. Then those spectral types of stars have become standard candles. For any spectral type of main sequence star, we know what its luminosity is. Then, when we look out farther than 1,000 light years, farther than what stellar parallax allows, we look at a star, we can examine its spectrum and see that it's, say, an M7 star. Well, being M7, we now know its luminosity. We can measure its brightness, and that tells us its distance. So standard candles are very important in astronomy for measuring distances. If we have a means of determining what an object's luminosity is, we can solve for its distance. Thought question: which kind of stars are best for measuring large distances? And so we're going to go with high luminosity stars, because low luminosity stars, the farther away they are, the dimmer it is. We might not be able to see them at all if it's very far away. So you think about if we want to measure distances to other galaxies and you're trying to pick out a dim star that's in another galaxy, that's going to be hard to do. But if we can find a very bright light, a high luminosity star in a distant galaxy, it'll just be easier to see. You learned in chapter 15 about variable stars. Now, there's a particular type of variable star called Cepheid variables, and Cepheid variables are just the ones that are the brightest ones. There are many different types, but Cepheids are important because they're the brightest variable stars. Because the period of Cepheid variable stars tells us their luminosities, we can use them as standard candles. So if you remember back to lecture in chapter 15, I showed that for variable stars, there is this period luminosity relationship. The longer the period, the time it takes to go from bright to dim to bright, the brighter it is. And we have an equation that we use to plug in the time, what the period is, and it tells us what the luminosity is. So any variable stars are standard candles. And here we have a graph of many data points for different stars. Here we have on this graph, the horizontal axis is the period in days, and then we have luminosity measured in solar luminosities. So let's take, for example, right this point where my marker is, right there, and it has a period of, looks like maybe 2.5, something like that, 2.5 days, and it is 1,000 solar luminosities. Then we go to one maybe about right here that has a longer period, 1 month, 30 days, and we can see it's got about maybe 12,000, 13,000 solar luminosities. The point is, the longer the period, the higher the luminosity, and we can tell what the luminosity is based on this relationship. Another standard candle is a white dwarf supernova. They make excellent standard candles, and here is a picture of a white dwarf supernova near its peak brightness next to a galaxy. You can see that its brightness is comparable to the brightness of the central bulge of that spiral galaxy next to it. Just to remind you, this is from chapter 18, The Bizarre Stellar Graveyard, White Dwarf Novae and Supernovae. The idea here is that if you have a white dwarf and a companion star, then if the stars are close enough to each other, then there'll be a mass transfer from the big red star. Usually it's going to be in a giant phase. So it grows so big and can barely handle onto those hang onto those outer layers. So the outer layers of hydrogen go onto the white dwarf. The hydrogen-rich gas spills into an accretion disk and forms a shell of hydrogen on the white dwarf. And as that shell builds up, the temperature of the accreted matter eventually becomes hot enough for hydrogen fusion. Fusion begins suddenly and explosively, causing a nova. And then you can have a white dwarf supernova. Again, you learned about this in chapter 18. If that hydrogen gas builds up on the white dwarf, and the white dwarf exceeds 1.4 solar masses, its electron degeneracy pressure cannot hold up under gravity. And so if it gets to the point where before it can go nova and get rid of that hydrogen shell that's built up, if it just gets up beyond 1.4 solar masses, the entire star will collapse. And this is what's called a white dwarf supernova. So down here at the bottom of the page, white dwarf supernova is where carbon fusion suddenly begins as the white dwarf in a close binary system reaches the white dwarf limit, causing a total explosion of the white dwarf. It's a very powerful event. Now, don't confuse this with a massive star supernova. You learned about this in chapter 17 in the life of high mass stars. This is where the iron core of a massive star reaches the white dwarf limit and collapses into a neutron star, causing an explosion. This is the first type of supernova that you learned about in this class. But right now, I'm talking about a white dwarf supernova as a standard candle. The really neat thing about this is they all happen in exactly the same way. You've got a white dwarf, and it is with a shell of hydrogen gas around it, and it gets to 1.4 solar masses. So there isn't too much variability, at least that we've discovered yet, between white dwarf supernovae, which means when they explode, they all have the same predictable luminosity. So if it's a luminosity that we know, then it's a standard candle. This goes back again to chapter 18. One way to tell supernova types apart between a massive star supernova and a white dwarf supernova is we look at the light curve showing how the luminosity changes. So the red shows a white dwarf supernova, and it's the same luminosity throughout the universe. When a white dwarf supernova happens, it always looks like this, and it's always the same. That makes it a standard candle. The difference between a white dwarf nova and a white dwarf supernova is that supernovae are much, much more luminous. They're about 100,000 times more luminous. With a nova, you have hydrogen that's turned into helium by fusion of the layer that's accreted onto the white dwarf. And the white dwarf is left intact after that little explosion happens. With a supernova, it's a complete annihilation of the white dwarf. The entire thing fuses, and there is nothing left behind. So back to this picture I showed, we see something like this. We recognize by its light curve that this is a white dwarf supernova. So we know its luminosity. It's a standard candle. We can measure its brightness with a photometer, and it gives us a way to measure the distance. And in fact, this is a method that's commonly used to tell the distances to other galaxies. Here you can see some before and after pictures. Along the top row, distant galaxies before the supernova, the same galaxies after the supernova, and the arrows point to the supernova. The apparent brightness of a white dwarf supernova tells us the distance to its galaxy, and this method is good for up to about 10 billion light years, which is almost across the entire span of the observable universe. Which brings us to Edwin Hubble. How did Hubble show that galaxies lie far beyond the Milky Way? Here he is at the Mount Palomar Observatory in the 1920s. The puzzle of spiral nebulae. Before Hubble, some scientists argued that spiral nebulae were entire galaxies like our Milky Way. Others maintained that they were smaller collections of stars within the Milky Way. So people had seen these spiral things. We now call them spiral galaxies, but they didn't know that they were galaxies. Even the Andromeda galaxy can be seen with the naked eye. People had seen that since ancient times, maybe not very clearly. The picture down below is a photograph of the Andromeda galaxy taken in 1899, and up and to the left is a little elliptical companion, but they never knew that these were galaxies. They knew of the Milky Way galaxy and just assumed that all these spiral things out there were nebulae inside our galaxy. The debate as to whether they were just nebulae within our galaxy or other galaxies remained unsettled until Edwin Hubble in the 1920s finally measured their distances. In the 1920s, Hubble settled the debate by measuring the distance to the Andromeda galaxy using Cepheid variables as standard candles. So he was able to measure that the Andromeda galaxy is about 2 million light years away. Now, they already knew that our galaxy was something like 100,000 light years across. And so then they were seeing that this Andromeda galaxy is much farther than the size of our own galaxy. And then they started looking at these other spiral nebulae and realizing those things are very far away. They're not nebulae, they are entire galaxies. And since that time, now it's become standard for us to measure the distances to galaxies using not only Cepheid variables, but also white dwarf supernovae. And when we use the two different methods, we can look at one galaxy and use the Cepheid variable method, looking at Cepheid variables throughout the galaxy and using the period luminosity relationship, and those show us what the distance is. We can use the separate method of white dwarf supernovae and see how far does that method tell us the galaxy is, and the results come out consistently when we try to determine the distances to galaxies. Well, on this picture right here, we've moved from radar, parallax, Cepheids, distance standards, which is just standard candles. And now we come to this last one, Hubble's law. So let's get into Hubble's law. Here you have a chart that Hubble made as he was measuring the distances to different galaxies. So here we have 0, then 10 to the 6 parsecs, so that's 1,000,000 parsecs. Remember what a parsec is, 3.26 light years. So we're looking at a distance of 3.26 million light years away. Here, 2 million parsecs, so that's going to be 6.52 million light years away. And on the vertical axis, he was looking at the speed that they're moving away from us, 500 kilometers presumably that's per second, 1,000 kilometers per second. What he found, as you can see on this graph, that there's an upward trend as the galaxies are farther away from us, they are moving faster away from us. And that became a very important discovery in astronomy, this realization that the farther away galaxies are, the faster they're moving away from us. And this led to the idea of that the universe is expanding. That's what happens in an expanding space. Something farther away is going to be moving faster from you. Not only was there that general realization, but he could also come up with a mathematical relationship from this chart and charts like this, a mathematical relationship so that if we know the distance, we can know the speed. If we know the speed, we can know the distance. There's an equation that governs those. Now, by the way, if you're wondering, how did he measure the speed that they're moving away? Well, I'll refer you back to chapter 5, where you learned about the Doppler effect. The Doppler effect, remember that if something is moving away from us, then its spectral lines are redshifted. And the faster it's moving away from us, the greater the redshift of those spectral lines. So we can actually see hydrogen lines, for example. We know exactly the wavelength of hydrogen lines, but we look at a galaxy far away, and we see all those hydrogen lines, but they've been shifted towards lower frequencies. So we can measure how much the shift is, and that tells us how fast the galaxy is moving. And this is what Hubble did 100 years ago. So here we have a particular galaxy originally emits this spectrum of light. So you can see all these different spectral wavelengths. And now, but the spectrum we observe from it is shifted by 5% to longer wavelengths, indicating that the galaxy is moving away from us at 5% of the speed of light. So we see all the regular spectral lines of hydrogen, helium, all the ones that we normally see in stars and galaxies, but they've all been shifted, and it tells us the speed. The spectral features of virtually all galaxies are red-shifted, which means that they're all moving away from us. I say virtually all galaxies because the galaxies that are in our immediate local group, like the Andromeda, the Large Magellanic Cloud, they are gravitationally bound to us, so some of them are actually approaching us. But if you get beyond our local group, you see the galaxies moving away from us. By measuring distances to galaxies, Hubble found that redshift and distance are related in a special way. The farther away a galaxy is from us, the faster it's moving away from us. Here's Hubble's law, and it's based on a similar chart to the one you saw before. Distance in millions of light years and recessional velocity, how fast it's moving away from us in kilometers per second. Hubble's law says that the speed something is moving away is some constant. That constant, we call it h naught or h sub 0, and that's what's called Hubble's constant times the distance. And it's based on, this goes back to basic algebra, that Hubble's constant is just based on the slope, how steep this line is. It says the solid line indicates the most likely value of Hubble's constant. The dashed lines indicate the approximate range consistent with observations, which is from 21 to 23 kilometers per second per mega light year. All right, what this means is they don't know exactly what Hubble's constant is. It's somewhere between these dashed lines, somewhere between about 21 and 23. Real quick, let's look at those units. 21 to 23 kilometers per second per mega light year. That means that for every million light years, every mega light year that a galaxy is away from us, it's moving away from us at an additional 22 kilometers per second. So if it's 1 million light years away, 22 kilometers per second. If it's 2 million light years away, it'll be moving away from us at 44 kilometers per second. We won't in this class get bogged down in the math or doing those calculations, but the point is we have a good assessment of this relationship between the speed something is moving away from us and the distance. Now we can measure speed based on the redshift of the spectral lines. We plug it into this equation and we can solve for distance. And here you can see the equation. So the redshift of a galaxy tells us its distance through Hubble's law. And this is the Hubble equation, but solved algebraically for distance. The distance is the velocity divided by Hubble's constant. This gives us a good assessment of distances far across to the other extreme, the other end of the observable universe. We can measure something's velocity by redshift. Our Hubble's constant, there's a plus or minus to that, as there is with all measurements. We don't know it exactly, but it gives us a fairly good assessment of distance. The distances of the farthest galaxies are measured from their redshifts. We measure galaxy distances using a chain of interdependent techniques. What that means is, you think back to Hubble's law, that assessment of distance relied on knowing what Hubble's constant is, that h naught. But how do we know Hubble's constant? Well, we know it because we're able to measure the velocities and distances of galaxies using white dwarf supernovae, using Cepheid variables. And how do we know how bright those Cepheid variables are? Well, it all goes back to stellar parallax. So it's a chain of interdependent techniques. And the more accurately we can measure stellar parallax, that gives us more accurate assessment of luminosities. That gives us a better ability to more accurately use the Cepheid variable method. That gives us a better ability to more accurately use Hubble's law. So all these methods are built on each other. In this video, what have we learned so far? How do we measure the distances to galaxies? The distance measurement chain begins with parallax measurements that build on radar ranging in our solar system. Using parallax and the relationship between luminosity, distance, and brightness, we can calibrate a series of standard candles. We can measure distances greater than 10 billion light years using white dwarf supernovae as standard candles. How did Hubble show that galaxies lie far beyond the Milky Way? He measured the distance to the Andromeda Galaxy using Cepheid variable stars as standard candles. And what is Hubble's law? The faster a galaxy is moving away from us, the greater its distance. And it's based on this equation: velocity is Hubble's constant times the distance. As we close up this video and this chapter, our study of cosmology, or the introduction to cosmology, I want to talk about how we assess the age of the universe. I started this video telling you that our assessment of distances can lead to assessment of time, assessment of age of the universe. I want to get into, briefly, a variety of methods that astronomers use to estimate how long the universe has been around. So these questions first come up: has the universe always existed, and how long has it existed? And we will talk more about this in a later chapter when we look at the birth of the universe and how we discovered that the universe actually had a beginning and how long it's been around. Astronomers estimate the age of the universe to be approximately 13.8 billion years. Keep in mind also, thinking back to chapter 8 when we were studying the formation of the solar system, we assess the age of the solar system based on the rocks that we study, radiometric dating, the age of the solar system to be 4.6 billion years. So the solar system is much younger than the universe itself. So let's get into how does Hubble's law tell us the age of the universe? The expansion rate of the universe appears to be the same everywhere in space. We see that the universe has no center and no edge as far as we can tell. Hubble's constant tells us the age of the universe because it relates the velocities and distances of all galaxies. Now remember, at the beginning of this video, I was using this analogy of somebody driving a car and saying, I've come a few miles, and we estimate that they've probably been driving for a few minutes, or if someone says, I've been driving for hundreds of miles, we estimate they've been driving for several hours. And it's really based on this, that the time is the distance divided by velocity. So here we're not talking about the time someone driving, but rather the time that the universe has been expanding. And so we assess the age of the universe to be the distance that things have gone divided by the speed. And in math that's a bit beyond the scope of this course, what it comes out to be is that that is proportional to 1 over Hubble's constant. And again, we will not be doing that math. We will not be doing these calculations, but I just want you to see that there are these relationships mathematically, that the Hubble's constant is related to the approximate age of the universe. Why does the observable universe have a horizon? There's something called the cosmological horizon. It marks the limits of the observable universe. It's a horizon in time rather than space. Since looking far away means looking back in time, there must be a limit, the beginning of the universe. So if you look 100 light years away, you're seeing 100 years ago. When you look 1,000,000 light years away, you're seeing 1,000,000 years ago. Well, if the universe had a beginning, there is a distance limit. What we call it the size of the observable universe, and that is the cosmological horizon. We can't see, for example, 15 billion light years away, because that light would have taken 15 billion years to get to us, and the universe hasn't been around that long. So there's a horizon that we can't see beyond because there hasn't been enough time. What have we learned? Why does the observable universe have a horizon? We cannot see back to a time before the beginning of the universe. As we assess the age of the universe, I want you to remember that to assess the age of the solar system, we use radiometric dating of rocks and meteorites, and we find that the solar system is about 4.6 billion years old. We can also do radiometric dating of stars. It's a little trickier, but we can look at the spectral emissions of stars and look at the ratios of different isotopes. The result is that we see that the oldest stars are between about 10 and 20 billion years old. So there's a plus or minus in there with the technique, but that gives us a range. So a question comes up. If M stars can live for up to 1 trillion years, why have we never found any that are that old, that are even 100 billion years old, much less 1 trillion years old? Why is it that all M stars that we see are still in their infancy? And the reason is that the universe hasn't been around for 1 trillion years, for 100 billion years, for these stars to age too much. So it's setting an upper limit on how old the universe is, or at least how long it's been since stars have been forming. Another method we use, you learned about this in chapter 15, is the main sequence turnoff point for star clusters. And you look at the HR diagram for a cluster where the O stars have all gone away, and the B stars and the A stars, O, B, A, F stars, and right about there is the turnoff point. This is the HR diagram for a very old cluster. And what we see is the oldest clusters that we found are between 11 and 13 billion years old. We can also do assessment of the oldest white dwarfs based on their rate of cooling. Remember that there are white dwarfs because they're hot, they're white, but we don't see any that have faded to become yellow or orange or red because there hasn't been enough time for those white dwarfs to cool. And the result is that the oldest white dwarfs we find are about 12 billion years old. So you can see this consistency of results from a variety of tests that we use on stars around the galaxy and even beyond our galaxy, that we see that the oldest stars are somewhere in the range of between 10 and 20 billion years, and more centering on about maybe 12 or 13 billion years. Putting all the data together, it seems that the universe is approximately 13.8 billion years old, and that the solar system was formed when the universe was about 9 billion years old, or 2/3 of its current age. So going back to this timeline that I showed you in a chapter 8 video, timeline of the universe, we have the moment of creation. There it is, let there be light, the universe was created. And then in the first billion years or so, the galaxies were forming. Milky Way galaxy was formed. And then a lot of time went by. To about 9 billion years, the universe was when the solar system formed. Now, if you think, why all this time? Well, you think the original stars, the original gas in our solar system, in our galaxy, only had hydrogen and helium. And so any star system that would form with just hydrogen and helium did not have the ingredients necessary for life. For life, we need carbon, nitrogen, oxygen, phosphorus, all these heavier elements. So the first generation of stars died away, and it had fused heavier elements. And then there's another generation of stars and another generation of stars. And with every generation of stars that passes over these billions of years, there's more chemical enrichment of the interstellar medium, where heavier and heavier elements are put out there. So that you get to where the universe was about 9 billion years old. And finally, in our region of the Milky Way, about 27,000 light years from the galaxy center, there was enough in this cloud of gas and dust, not just hydrogen, helium, but carbon, nitrogen, iron, oxygen, gold, silver, all these elements that we have on Earth. And so finally there was this solar system formed, and here we are. And then here we are in the present day, about 13.7, 13.8 billion years down the line from the original creation. That is the end of Chapter 20, Galaxies and the Foundation of Modern Cosmology. Have a great day.